In this course, we don't get too technical about limits. It's enough for us to answer most of our questions using a fairly rough intuition, and we'll express it here. The idea is when we state that the limit as x approaches some number, and we have a function, if that equals L, what do we actually mean when we say that? We can say that if we can make the function as close to L. So isolating the function and the L value, those get closer and closer to each other, or can be made as similar as possible, as long as we pick x values that are close to that C value. We'll see this through some examples to make this a little more concrete. Note though that it's possible that this number L may not exist. In other words, there might be nothing that we can write on this right-hand side that makes any sense or satisfies this definition. If that's the case, we would say the limit does not exist. Sometimes, more colloquially, we might say that f of x, the limit of it, equals infinity, or I usually prefer to say approaches infinity. It's always risky to say something equals infinity. So we might say that if we know in particular that our graph is going off towards a vertical asymptote. Sometimes it's a little more expressive, but the limit does not exist is also true, and we'll accept both answers in this class. The important distinction to make here is that the limit never depends on the value at the point. In other words, the limit's all about where would I end up if I had no idea of the function's value at the point I'm actually approaching. The function can do something else, I don't care. As long as I'm approaching this value, then that's my limit value. That's my L, is where I would have ended up regardless of what the graph does at the point. Let's take a look at an example to see how that works in practice. Looking at this graph here, notice the little hole and the value 6 here. This is all occurring around x equals 2. And here we're asked to say why the limit as x approaches 2 of the function is not 6. Well, let's go back to our definition that we just introduced. If we were to say this, that's true if for x close to 2, the f of x values are close to 6. There's some idea of getting closer and closer to, but that's the key idea, is that if we're close in x's to 2, then our y value should be close to 6. And we can see pretty easily that that's not the case. If we pick x values that are close to 2, but not equal to 2, then we're going to get y values that are much closer to something else, but definitely not 6. We're going to get these kinds of y values back. With that picture in mind, it leads us to our next question on the next page. Describe the real value and the limits for x equals 2 of the graph. What we can say from our last sketch is that as x approaches 2, what does our function approach? Well, we can see as my x values get closer to 2, the y values get closer and closer to that empty circle, which is at y equals 4. And that's the same on both sides. If we walk down this graph, we're getting closer and closer to 4. What's the difference though? What about the black dot? That is simply the function value at x equals 2. That is exactly equal to 6. This is a statement about limits, and this is a statement about the function value at a single point. This is at x approaches 2, where we explicitly don't care what happens at 2. That is the empty circle. And then if we say, no, I'm going to go right to 2 and look at the graph, that's this statement here, and it gives us a perfectly reasonable value as well. It just happens to be different from what the limit is. In this example, we have a limit that exists. Let's contrast that with some other examples on the next page. Consider this graph here and ask yourself, what is the value of the limit as x approaches 0 on this graph? Think about it for a moment, and then we'll come back. All right. Well, for this function, the limit as x approaches 0, if we were to say that that was equal to some number L, remember that this would have to be a real number. That's where we say the limit exists, if we can get some real number. But no matter what real number we pick, if we pick an L value there, if we get closer to 0, our graph's going to keep going up. And we're not going to get closer and closer to L. We're in fact going to get further and further away from it. And all it takes is a tiny little step in X for that to happen. So the problem here is that there's no finite limit. And as soon as there's no finite limit, we say the limit does not exist. We're only going to take real numbers as possible answers. Now take a look at this graph down here and ask yourself again, as this graph approaches 0, and it's a graph that has these oscillations that are increasing in frequency, why does the limit as x approaches 0 of this graph not exist? Take a moment, then we'll come back. All right, so here, it's definitely not the same problem as the last question. All the values here are within a certain range, and so the limit would be finite because the function values are all finite. However, it does not approach a single value. In other words, if you picked any value on the axis here and said, that's my L, well, as we get closer and closer and closer in X, we're going close to L, but then we're going away from it. Then we're going close to L, then we're going away, close to L. And so there's no single value that we're approaching. And that means if there's no single answer, then we say the limit does not exist. And so we'd say the same thing here just to make it explicit. Both of these suffer from that. It's not really deficiency, it's just a statement about what we know about the function value as we get closer and closer to 0.